or Dylan? Who's coming in? Dylan. All right, and of course, I'm sorry, it just skipped my mind, the homework, so I didn't get it up until this morning. There is homework for Wednesday. It really, honestly, should be the easiest homework you've had. 4 of the 5 questions are from the first section of questions. I think they're conceptual questions or review questions or something like that. They're ones where you just find it in the textbook and write it down. What? Huh?
Is there a statistic problem?
We've never had a statistics problem here.
Well,
You mean calculus? We had some calculus in there.
We have never had a calculus problem either.
Yeah, we did.
just that's pretty.
We had that one, like at the beginning of the semester. It wasn't all that hard.
Calculus?
It wasn't more like an algebra application. We've never had
Yeah.
a calculus problem.
We've never done an integral or derivative, hence no calculus. Anyway, one question I think has to use Kepler's third law. Did you have a question, Sarah? No, I'm just looking at the hand.
Getting comfy with my pencil.
Okay, getting comfy with it. All right, one last thing on the Earth before we leave the Earth and start talking about other objects in the solar system. And that is the Coriolis effect. How many people know the Coriolis effect?
Like I'm personally. We've met.
I see we're in a rare mood today. Okay, the Coriolis effect is, well, you may believe that toilets flush the direction they do because of the Coriolis effect. The fact is it's not that strong. They make the toilets so they will flush that way because there is maybe a 0.5% or percent preference for it to go that way. But it's not that strong. But the Coriolis effect is strong when you have a large system. And so we will look here in the pictures to get an idea of the Coriolis effect. If you are on the equator of the Earth, because the Earth is rotating, you're actually whipping along pretty quickly. Right? We could calculate things out. We know it takes 23 hours, 56 minutes, and 9 seconds, or 4.9 seconds, whatever it is, for the Earth to do one rotation. And so if we take the radius of the Earth, 2 pi r would be the distance. We can calculate the speed. I'm not going to do it right now. But we're moving pretty quick at the equator. So if you're at the equator and you throw a ball straight north, that ball isn't just going north. It's also going to be going east because we're traveling eastward.
You mean? Yeah.
Yeah. So the ball is going east and north. But as the ball goes farther north, you're getting closer to the axis of rotation. And so it's like if you're on a merry-go-round. Is that the right thing?
Yeah.
Okay, the thing they have in the park.
The ones they took down.
Yeah, because kids would fall off and break their heads.
Carousel or merry-go-rounds in there.
Huh?
Carousel or merry-go-round.
Well, the one that you can go fast and have fun on, not the one where you sit in a little horse and go.
That would be the merry-go-round that we're talking about.
Okay. Anyway, as we know from that, if you go toward the center, you go slower. If you go on the outside, you go faster.
Oh, yeah.
Spoken like the person who holds on and swings his butt out as far as he can.
Lift up my legs and just take off.
Yeah. Anyway, so as the ball goes closer to the axis of rotation, the Earth isn't traveling as fast anymore. But the ball is still going to be going east with the same speed. So compared to the ground, it's going to look like the ball deviates and starts going like that. It's because it was going to the east, and as you go farther north, its speed to the east becomes faster and faster compared to the Earth's speed. Now, if you were on the North Pole and you did the same thing, you threw it south from the North Pole, it would have virtually no speed going east. As it goes farther from the pole, the Earth is going faster, so compared to the Earth, it would appear to deviate like that. Yes, question, Satish.
this assuming that you can throw it from outside of the atmosphere, like so that you're not
No, this would work if you were, I mean,
high enough up?
if you're using an
Ballistic.
ACB or ACBM.
Something basically
Yeah.
that could shoot far enough to test it.
Yeah, yes.
Oh.
It needs to be, I mean, obviously you can't throw it far enough to test this. But yeah, a ballistic missile, yeah, it would affect. There's a story I used to tell about doing military games and going to the southern hemisphere. If you threw it south, it would go the opposite direction. But further calculations say that the story is an exaggeration. So, a story about them missing by a long shot because the Coriolis effect was calibrated only for the northern hemisphere. But it turns out, when you calculate it out, it can't be true. Okay, why do I bring up that Coriolis effect here?
We're talking about Jupiter next.
It is something that's relevant for Jupiter because Jupiter doesn't have this action going on. On Earth, because of this effect, we have our storms that basically start at the equator and move outward. So you have the storms are coming up like this or going down like that. And as they move, it causes a rotation. And so we have cyclonic storms, that is storms that twist or rotate. And the direction they rotate is opposite in the northern hemisphere as it is in the southern hemisphere, because in both cases, as you leave the pole, leave the equator, go toward the pole, it's going to go east. So the cyclonic storms we have on Earth are caused by this Coriolis effect. Now, because somebody said Jupiter, I don't remember which one of you it was. On Jupiter doesn't have a hot equator and a cold pole. Because it doesn't have the hot equator and the cold pole, you don't have the storms going from the equator toward the pole. And because you don't have the storms going from the equator toward the pole, you don't have cyclonic storms. You would still have the Coriolis effect if you had winds going that direction. But instead, Jupiter and Saturn, the gas giants, they have what we call belt zone weather patterns. Their weather patterns go all the way around the planet instead of doing little cyclones.
Why do some years there's lots of typhoons and other years there's all the typhoons just pass you by?
Okay, it's very complicated and far beyond what I understand, but it has to do with the jet streams in the ocean. Those jet streams change and you get higher temperatures and lower temperatures in the ocean water as a result. The jet streams are taking cold water from Alaska. They actually come down around the continent, come back up, go under themselves, come back around. And those vary with time. And that's what causes, being from California, I'm familiar with the El Nino and the La Nina. This year is supposed to be an outrageous El Nino according to predictions. And
Actually getting some rain?
have you not been reading the news?
No.
They had to close I-5 because of the flash floods that brought mud flows in and buried the cars.
Rain is good. After
Yeah, rain is good. Actually, for anyone who cares, our almond crop this year was pretty good. But because it was like everybody got 3/4 the almond crop last year, the price shot up. So we're getting more than $4 a pound for almonds this year.
Crap, my almond was
The price like 5 years ago that we were getting was under $2 a pound. So you should expect your price at the supermarket to shoot up soon. Just in case you care. But you know what that means for my family? That means we only have 40 acres in almonds, and my dad is getting more off of the almond lease than I make a year. Just 40 acres. Yeah, it is.
That's really good. Wow.
Yeah.
Can I be adopted?
Okay, so here's a picture showing how the Coriolis effect causes us to have these cyclonic storms. And so why is this important? Because we're going to compare, it's going to be important when we talk about Jupiter and Saturn that don't have these cyclonic storms. That must be Tioni. Okay, now going to the moon. When you look at the moon, you see these dark regions like Okay, let me change because blue doesn't stand out as much as I would like. Magenta will stand out nicely. You see this dark region here, right?
Yeah.
When people look at the moon, you can see that the moon has features. So for a long time past, people looked up there and you compared it to the Earth, and they said those dark regions, they look like the oceans on Earth. And so they called them seas. Well, Maria is the name, the Latin word for a sea. So actually it's mare. Mare is singular, Maria is plural. So these are called seas, Maria. And then, of course, now we have telescopes and whatnot. We can see more clearly. We see, wow, those aren't oceans, but they still maintain the name. Now, when you look at those regions, what sets them apart? Primarily, they're lowland regions that are smooth surfaces, relatively speaking. They're smooth surfaces that have been flooded with lava to make them smooth. So one of the main features we notice on the moon are those Maria. We also have plenty of craters, and you can see all kinds of cratering here on the moon. And the moon has highlands. Now on Earth we have highlands, the mountain regions, and we have oceans, and the Maria would fill the niche of the ocean. So we have similar types of land structures on the moon as we have on Earth. Question?
Yeah, it's my understanding that what you're talking about right now is like the main visible difference between that and Venus. Is that true?
Oh, wait, you've already turned it in. The textbook listed, actually I read it as 3, you might have considered it 4 primary differences, and they were things like the walls of the crater are steeper on Moon and less steep on Mercury. What were the other differences? The craters are, I think, closer together on Mercury. I wish I could remember these. But there are a number of subtle differences. The lobate scarps is the biggest one, but it wasn't one of the ones listed as the primary differences. But when you look at Mercury, and I'll show a side-by-side picture from the textbook of Mercury versus the moon, they look very similar. And they look very similar for a very simple reason. They both don't have any atmosphere. And since they don't have any atmosphere, they get peppered by any debris that happens by. And so one of the features that's not on here is, well, actually, I think I have a picture of, here's pictures of craters, blah, blah, blah. You see lots of craters, lots of impacts. Yes, this is on the moon. What?
Pancake in the morning?
No, the pancakes are on Venus. I've got a picture I want to show you. Okay, well, let's just answer this. This was a question. Whoops. This was a question to make sure that you were paying attention. Right now, only Dylan and Lauren are in because of my fumbling on the keyboard. And Sarah now.
I think I brought it.
Do you have yours, Tierney? Okay. Yeah, he's in now. Okay, so we had 12 people for Maria, 1 person for Crater. I'm not even going to write that down. The Maria is a sea. They call them that because of the dark look. Now, if you look at this map, this is a map of the moon. It's not what we're used to seeing the moon look like. Why? It's flat. We had a lab where we dealt with looking at the Earth map. We usually see it as flat, but it's actually a globe. We noticed that on the flat map, it looks like Iceland is really big. But on the globe, you see it's not as big as it would appear on the flat map because the closer you get to the poles, the more you have to stretch it to make it flat. Question, Seth?
Is this the visible portion or the?
This is going over the whole moon. So this is taking the globe, flattening out. And so it looks quite a bit different. And there's a lot of detail that you can't see. I think I have a picture that shows the side of the moon that always faces us compared to the other side. And they do look very different. If it's not on the next one, I'm going to give up. It's not on the next one. Okay, I don't give up. I don't have... Here's the picture that shows the two. The side that faces us, the side that doesn't. The side that faces us, it's the left one, right? You should... What? Yes. The side that doesn't face us has virtually none, right? What does that mean? That means it's had a lot more recent impacts. Recent impacts so that anything that had flooding with lava has been impacted again, erasing essentially the flooding region. You do have the highlands. The highlands have a lot of craters. The lowlands, of course, is where you have the seas. One might ask, why does this side of the moon have so many fewer impacts than this side? There are a number of theories. One that seems to make sense to me is that the moon is in a locked orbit. One side of the moon always faces the Earth. And so debris that comes from that side is going to be caught in the Earth's atmosphere and not make it to the moon. So the Earth would be doing some protecting of that side. I believe that's why that side has fewer craters. It makes logical sense to me. Notice the statement, why is the far side not the dark side of the moon?
Because it gets hit by the light whenever we get a new moon.
Yeah. Whenever we have a new moon, the other side of the moon is the bright side of the moon. The side we see is the dark side. So I tend to say there's still a dark side, but the dark side isn't a fixed side. It's just the side that isn't at that moment getting light. Some people use the term the dark side of the moon to mean there is a side that never gets light, and that would be incorrect. Lauren Lee has a question.
Why did God make the moon?
Why did God make the moon? If I could know the mind of God, I probably wouldn't be a mere human anymore. So I don't know. We will talk about in just a moment the scientific theory, actually just a moment, I think it's the last slide, on how the moon came to be. No, it can't be the last slide. Last slide on the moon. We'll talk about the scientific theory of how the moon came to be. But that's a scientific theory based on, assuming that things that God created things. Well, I see the scientific theory as assuming that God created the universe with the Big Bang.
What's the purpose of having a moon?
What's the purpose? Once again, I don't know the mind of God. I cannot tell you the purpose of having, even things like hair. We believe we understand why we have hair.
To keep our head warm.
Yes, to keep our heads warm.
So if you're bald, it's game over.
Careful now. This could happen to you too.
Yes.
I meant people who are generally completely bald, like Tyler Morrison.
Anyhow, I can't say why.
Okay.
Science will give you an answer that, for something like this is just, well, that's the way it came about because of the laws of physics.
Maybe God thought that times were
Okay, I really, really want to look at some of these features. These things here are the things called the rills. You see these little things. They're basically lava tubes like they have in Hawaii. Not active flows on the moon anymore.
Is there atmosphere in the lava tube?
I thought the moon has, nothing like a river, no water, no lava or something.
Okay, I don't think I have any pictures to go along with this, but let's talk about that just for a second. Is there water on the moon? Yes or no?
probably not. It would evaporate.
Okay, probably not, it wouldn't evaporate. But what if it froze?
Yeah, then it would probably be under the crust.
Then you could have it. It could be under the crust. A few years ago, they actually did an experiment to look for water on the moon. What did they do? They crashed an object into the moon.
Why do people hate the moon so much?
They crashed an object into the moon, and then they looked at the material that flew off of the moon because of that, and looked for the absorption spectra to indicate water vapor. Because their theory was that there should be frozen ice in regions that are permanently in shadow. And so they wanted to look for that, and they found some. There definitely is some H2O on the moon, certainly not in liquid form, in ice form. Now, lava. What about lava? There is no current lava on the moon, but if you have a major impact, there will be major heating that goes along with that impact. That major heating could produce molten rock. You also have, in the past, the moon probably had a molten core, probably had a magnetic field, and had magma that could flow. So things it once had and doesn't have, magma would be something that it probably once had a fair amount of and doesn't have much anymore. The moon does not have a magnetic field, so it doesn't have what we need for magnetic field. Now, there are three things we need for magnetic field. Interesting. Black instead of white. Maybe that goes along. Remember how the full set of slides didn't load last time? Yeah. It happened again. I tried 3 different ways of loading them, and finally the third way worked, but apparently it gave me black instead of white backgrounds. So, for a magnetic field, what do we need?
Well, we need to have a dynamo or a core.
Geodynamo, which means that we have to have what Lauren Lee was starting to say, I think. We have to have a liquid core that is conducting material. And there's one more thing that is
Convection.
not as easy to remember. It needs to have convection. Now, with the moon not having a magnetic field, the theory is that the moon is probably frozen. That is, it no longer has a liquid core. Why did they come up with that? Because the rate at which something loses heat is proportional to its surface area. Now, the area of a sphere is proportional to the radius squared. The amount of heat it has is proportional to its volume, so proportional to the radius cubed. So the ratio between how quickly you're losing heat and how much you have is proportional to 1 over the radius. And what that means is, if you have a small object, you're going to have a pretty big amount of heat lost per total heat. So it cools quickly. The example in the textbook is you have, I mentioned this in class before, a piece of entree on your fork, it cools quickly. A piece of entree in the dish with all the rest, it cools very slowly. It's the same thing with these objects. So the moon should have cooled quickly, should have frozen. So the theory is the moon doesn't have a magnetic field, probably because it's missing that part. Now, when we get to Venus, we'll have no magnetic field, but they believe it definitely should have a liquid core, so it'll have to be something different.
So the moon doesn't have that liquid core?
Right. The belief is the moon must not have a liquid core. Now, if I get past the moon here, which I've got to be getting close to the end of my moon slides, I'll just have to... Yeah, okay. We're not to the end yet, so we still have a chance. I want to talk about the rocks on the moon, and I haven't gotten to anything that says the rocks on the moon, at least that I saw. Here is the formation of the Maria. You have a big impact. You break the surface. You have molten magma that flows over, fills it in. It's a very simple story, isn't it? It's, pretty straightforward. The interior of the moon is real. Okay, here's where it actually has the word I was looking for. White does not show up well on that slide. The word I was looking for was regolith. So here's what I'm going to actually talk about. I think the next slide will show a picture. we know about the interior of the moon because we've had a fair amount of interaction with the moon. We've landed spacecraft there, we've landed humans there. It's close enough that we can actually do some work from Earth to examine it. And one of the interesting things that's been found about the moon is that its core is small and not at the center.
I see that.
Its core is closer to the Earth. Now that actually makes sense. The moon, when it first formed, one would almost certainly assume that it was rotating. But if it's not perfectly uniform, and how many things are perfectly uniform? If it's not perfectly uniform, there's going to be more pull to try to make the more dense side stay toward the Earth. And so over time, its rotation slows until it got locked in with the side that was slightly more dense facing the Earth. Well, then you have a constant pull on the core that's pulling it toward the Earth and has slowly pulled it off-center. So its center is off-center because of its interaction with the Earth. You can see, like the Earth, it has a crust, a mantle, and a core, but probably not a liquid core. Now, other things to note here. The outermost layer is powdered rock called regolith. Powdered rock that's meters deep. Now, just thinking about logically, how do you go from solid rock, had to be solid rock when it formed, to powdered rock?
You have to hit it.
You have to hit it. And so it's had lots and lots of impacts. Now the Earth, when we do something like go through a debris field, we see meteor showers. The material, largely sized as a grain of sand, burns up in the atmosphere, doesn't hit us. But the moon doesn't have any atmosphere. So when we're going through a debris field, the moon is also going through that debris field, but it has nothing to protect its surface. So it's getting sandblasted. And so the moon's surface is largely powdered. It's covered with this regolith because it has nothing, no atmosphere to protect it from little minor impacts with tiny things. Here's a picture of a footprint in that regolith, and that footprint will stay there for a very, very long time. Why? There's no wind. There's no atmosphere, nothing to blow on it. Only thing that's going to mess up that footprint is impacts. And as long as they're tiny impacts, it's going to be very small changes over time. Now, if you have a big thing that hits the footprint, well, it's obliterated instantly. And the moon will have occasionally large objects that hit it. You know, large objects like a meter in size or something. So if the meter-sized object hits that, well, it's gone. Okay, the moon is now too cool to have volcanic activity. That goes along with what I was saying in answer to Labor's question. It has a small mass, so it has a small escape velocity, and thus gases can escape. And here's the statement about the ice. There is water ice and permanently shadowed craters at the lunar pole. Okay, I think we're just about ready to leave the moon, except for I haven't talked about its formation. Got to talk about its rotation, then I'll talk about its formation. I don't think I have slides on the formation, so when we get to Mercury, that's when I'll talk about its formation. It has synchronous rotation. That's what we call the rotation where it's locked, so the same side of the moon is constantly facing the Earth. They put a little nose on it. I'm putting a little green dot there on the nose. So the moon is orbiting, so we always see the same thing. Except the moon's orbit is not perfectly circular. It's elliptical, just like our orbit around the sun is elliptical. But if you have an elliptical orbit, what does that tell you about the speed of the orbit?
When it's farthest, it's the fastest, but when it's closer, it's the slowest.
Other way around. When it's farthest, it's the slowest. When it's closest, it's the fastest. You have the right idea. So the moon is not orbiting the Earth at a constant rate. But it is going to be rotating at a constant rate. Because it's rotating at a constant rate but not orbiting at a constant rate, that means it can't be perfectly locked on us. And so that's what causes the, quote, wobble. What was the correct word for that wobble?
The vibrato. No,
Libration.
Well,
It
yes,
librates.
it's vibration, but
It's
they had a
L-I-B-R-A-T.
Oh, vibration.
It librates. The libration is the slight changes in the viewing angle we see because its speed is speeding up and slowing down while its rotation is constant. So it's not a very big effect, but you do, and there are animations you can look at to show you how you have that small libration in what you see. Come on, be the end of the moon. Okay, where did the moon come from? I'm quite sure I don't have a picture to go along with this. I just have this statement. I'll go to the next slide after we're done in case it's there, but I don't recall having put one in.
Oh, we have to answer that?
Yeah.
There's lots of like arrays.
We'll talk about that. Remember, all of these are for you to think about. You're not being graded on being right or wrong. You're being graded on participating. Megan. Okay. All right, here we had 2, 4, 1, and 6. Clearly not a consensus, and that's fine because scientists have proposed all of these as correct answers. They're not all accepted, but they've all been proposed. They're all reasonable answers. So let's look at these. An independent planet was captured. That is, you had a planetesimal, grew, came close enough to the Earth as the Earth's gravity grabbed it and didn't let it leave. There are plenty of objects that are believed to be moons by that method. For instance, Deimos and Phobos, the 2 moons of Mars. That's believed to be the way they got to be moons of Mars. But examination of the moon suggests that doesn't really make sense. The moon is too much like the Earth to have been formed somewhere else. So then we have the second one, formed together with the Earth. Formed together with the Earth makes good sense. After all, we believe the whole solar system was formed at the same time. But if you examine the elements, there's enough difference that they say that one doesn't work either. So the elements are too different to have been captured, but too similar to have been formed together. Then we have spinning Earth threw off a chunk. Right? Potter's wheel example, if you spin out Potter's wheel too fast, your stuff will just fly apart, right? So that's the idea here. And as far as they can tell, no, never spun that fast. So then we get to the last one, the one that is the accepted one now. The Earth was impacted by a large object. The theory is the Earth was here doing its thing, minding its own business. Let's go to the next slide and see if there's a picture to go with this. I'm pretty sure, like I said, that I don't have one. Nope. So the Earth is sitting here minding its own business, just hanging out. We'll draw the Earth here.
Can it be a happy Earth?
I don't know if it can be a happy Earth. Don't worry. No, that's really what it's supposed to look like. Here's the Earth. Uh-oh. That's not what it's supposed to look like. There we go. So there's the Earth. And then some object comes flying in. So we'll have this magenta object come flying in. And it impacts, a major impact. Something that causes the Earth to shudder. In that impact, what's going to happen to the Earth?
It'll become really unstable.
It'll become really unstable. You'll have a lot of material that goes flying off of the Earth because of that crunch, right? That material will include a fair amount of this pink stuff as well as a lot of stuff from the Earth. And so what is theorized to have happened after that is you had a, let's make it blue. you had what was left of the Earth in here, and then you had a lot of debris, and I certainly won't go with black, a lot of debris out here that was orbiting around the Earth. So basically the Earth had its ring system at that point. A ring system caused because of this big impact. Now the material in that ring system would be most like what part of the Earth? What part of the Earth would it be most like? Remember, all you education majors, you're not supposed to ask those whiplash questions. You're not supposed to say it like the statement, then turn it into a question with the last word. Students' minds are in the wrong mode. Okay, most like the crust in the upper mantle. Because when it hit, of course, that's the first material that gets hit, it's the first material that gets ejected. So the material that is in orbit should be more like the crust and upper mantle and less like the core. And that's what we find in the moon. The moon has a lower density. It's very similar to the crust, not so much like the core. So the theory is that this debris out here that was a ring, because of gravity, it started coalescing to form the moon. So this is called an impact theory. Now remember, all of those hypotheses, all of the possible answers that we had here, those were all good scientific ideas that were proposed as answers for where the moon came from. And then following the scientific method, they looked at predictions from those different hypotheses and compared them to actual measurements. And they found reasons to abandon the top three.
I have another.
You what?
I have another theory.
Okay.
We have the asteroid belt. That was probably a planet that exploded for some reason, and like whatever the biggest part of it just like flew toward the sun, and then a piece of it hit the Earth, and then we have the moon. Yeah.
The asteroid belt is believed to have formed from being a planetesimal or protoplanet, but the mass in the asteroid belt is far smaller than the mass of a planet.
Right.
And
Which
so,
is why I'm saying that big mass probably flew toward the Earth and exploded.
well, it's believed the thing that hit the Earth would be more than what you have in the asteroid belt. Okay, moving forward. Mercury. Mercury is the innermost planet. Because it's close to the sun, it gets baked. So temperatures on Mercury can be very, very hot. Over 700 Kelvin, as you had in your Flip Friday, on a hot, sunny day. Around 70 kelvins, that's colder than liquid nitrogen temperature on a cold day. So it gets really hot and really cold.
Wouldn't you fall into one of the craters into the shadow and do the same thing?
What was that?
Wouldn't the same thing happen if you just fall into a shadow?
Yes, you could indeed have water ice in a shadow. Is that what you're saying? Same thing?
Yeah, even when you're in daytime.
Yes, yeah. If you're in the water ice, it will be cool. In fact, if you think about temperatures on Earth, our atmosphere has a big deal to do with our temperatures. If you go out to the desert, you probably know that during the daytime it's like 95, 110. At nighttime it'll be like 40 or 50, right? If it's clear, what happens if it's cloudy? It stays much warmer during the night. It may not be as hot during the day, but it stays warmer during the night because of that cloud. And so having clouds and atmosphere helps to keep the temperatures from fluctuating as much. So if you're on something like Mercury that has no atmosphere, its temperatures will fluctuate just light versus dark. If it's light, it'll heat up quickly. If it's cool, or if it's dark, it'll cool down very quickly. We have done a fair amount of exploration of Mercury. You see that there are some recent dates here. Messenger went to orbit around Mercury in 2011. So our information about Mercury is fairly recent. Its orbit is the most eccentric of any of our planets. Most eccentric means it's the farthest from circular, the most elliptical. So it gets as close as 0.29 astronomical units, or 29% of the distance between the Earth and the Sun, and as far as 0.41 astronomical units, 41%. That's a pretty big variation in its orbit. Because of that big variation in its orbit, it's definitely going to have noticeable speeding up and slowing down. To go along with Eliezer, where on Mercury would you look for water ice? It is all the same. I just think that's a funny answer. It is not all the same, in other words. Okay. All right, we had 1, 3, 8. Somewhere in a permanent shadow. That's where you're most likely to find ice because it's always cold there. Come on. Here's comparing the moon with Mercury. You look at those and you're like, wow, they really do look a lot alike. They both have lots of craters with lava flows. Mercury has fewer craters that overlap. That's, the differences. They have lower crater rims on Mercury due to the higher gravity. That is, they don't have as steep. They're shallower. But they're very similar in features. If you look at Mercury, you find that one feature of Mercury that's really outstanding is these things called lobate scarps. Our textbook just calls them scarps. What is an escarpment?
Is it a relief?
It means a cliff. So these lobate scarps, and here I will draw in green. So it has these cliffs. And notice that cliff cuts right through a crater. Now, of course, your job as a scientist, if you're to accept it, is to try to figure out things like what would cause that. And the scientific idea that seems to have stuck is that that's the result of shrinkage. We know when things are hot, they tend to expand. When they cool, they tend to contract. Especially true, Mercury, we believe, has more iron than most planets, higher percentage iron. And so if its iron core cools, it will contract and shrink. And it's believed that these scarps are the surface fracturing because the inside shrunk. So that's an important feature to know about Mercury. Mercury's magnetic field. Okay, got to answer this first. What do the lobate scarps indicate about Mercury?
I mean, that isn't wrong.
The answers are over the wrong one here, and I'm looking, I'm like, why is everybody answering? Oh. All right, we have 209,002. Okay, so the majority said its core has shrunk, and that is correct. The standard interpretation of those lobate scarps is that they're the result of the core shrinking. Why would the core shrink?
Because it cools down.
Because it cooled down, they believe it's iron, and iron shrinks a lot when it's cooled. So it's not the surface that's iron, it's the core is iron and is cooled and shrunk. Okay, I believe we were getting to, I know I was getting to magnetic field because I believe that's where my slides were going. Oh no, first we have this feature. The Caloris Basin is really cool to me for one reason, and it's not because it's a huge impact crater. The reason it's cool to me is that the impact was so significant that the far side, the opposite side of the planet, went as a result of the impact on the other side. Now, you know that happens. You've seen the little desk toy where you have the steel balls and you have them all lined up here. You pull this one up, you swing it down, it hits, and you have the collisions to go through, and the last one comes off. That's essentially what's going on there. You have a collision on one side, and the shock wave goes through that ball. When it gets to the other side, it hits the next ball, and it transmits until you get to the last one, and the last ball leaves because of the shock wave. You transmit it through. Well, that's what happens with a planet, too. But you tend to not think, the balls don't poof open on the other side, right? It's not that much force that's being transmitted with your shock wave. But here you have such a significant shock wave that it caused the other side to blow out. Whoops.
You erased it. It's like acne cream for a planet.
I fixed the blemish, yes. Okay. The size is 800 kilometers wide. I mean, we're talking, this is a crater bigger than we're not a big state here in Nebraska, but we're not a tiny state. It's
We're not Rhode Island or anything.
Yeah. But yeah, if we were, Texas would laugh at us, and of course Alaska laughs at Texas. So it's somewhere in the ballpark garage size. Please talk about magnetic field now. Okay.
Close enough.
No, not close enough. Right there. Mercury does have a magnetic field, but it's an extremely weak magnetic field. What was the amount compared to the Earth, since you guys did this on Friday?
90, was it? It was some exaggeratedly small.
I think it said like less than 1,000 the size of the Earth or something like that. It's an extremely weak magnetic field.
I read that the
That was
entire
Venus.
magnetic field fits inside the planet, right?
That was Venus that I was saying was the 1,000.
That was Venus?
They were saying because Venus spins so slowly.
The Venus has none.
I don't think it was Mercury though. There was that number.
But
They may have said it was really small, but it wasn't.
I could be wrong. But the theory on Venus, it has a very, very weak magnetic field. Before 2011, we thought it had no magnetic field. And then with the messenger, they found, hey, it does have something really, really weak. So that's the primary reason that we have a new textbook, because it has the new information about Mercury having a weak magnetic field. And so if it has a weak magnetic field, that means, well, what does it have to have? A liquid core, that is?
Iron or something.
That's conducting, it has convection. Okay, so it has to have, now the liquid core also has to be rotating. I guess I should have said that. It's a rotating liquid core. And so they say, well, the core must be largely frozen, but not completely frozen. Before 2011, when they measured that, they thought the core was just completely frozen. So that was a big piece of information right there, that it actually still has a really weak magnetic field. It may have some iron core there that's molten. Has a lot more, if you look at this, that doesn't look like the Earth at all, right? The core here is much bigger, the iron nickel core. So why is that? Don't really have a great answer, because if it could collect iron, it should have been able to collect the silicates. It's very similar temperatures for the condensation point. So not really understood. Maybe it's a result of collisions. What do you mean collisions? Well, here is a picture to illustrate the theory. That you had Mercury hanging out, and just like the Earth got hit, it got hit. Seems like we're talking a lot about things smashing into other things.
I'm telling you, something exploded out there where that asteroid got.
Well, it simply makes sense for in the early days of the solar system, there have been a lot of collisions because there were a lot of objects early on. But each time you have a collision, there's one less object out there. And so the collisions exponentially decline with time. So it makes sense to have all these collisions. So the idea is if there was just a significant collision here, and that collision knocked away much of the rocky mantle, so basically it took the exterior of Mercury away because of the collision knocking it loose, leaving mostly just the core. That's the theory.
So they think that Mercury used to be bigger.
Yeah.
And probably farther away from the sun.
We'll end up with the orbit of Mercury. Here you have a picture that shows how non-circular its orbit is. Because it's not circular, you can't have Mercury form a locked orbit like the moon has around the Earth. But it has the next best thing. It's set up a resonance. So if you look there, you see once again they put a little nose to show you the side of Mercury. And early on, you have that nose turning. And if you pay attention here, this was pointing directly at the sun. Now it's pointing a little behind the sun. You would see, if you were on Mercury, going from here to here, there's an 8-day period where you would see the sun have retrograde motion. What does that mean? Well, the sun's been rising, now it's noon. Now it's still morning before noon. Here we come, now it's past noon. That's what you would see on Mercury. Is that bizarre?
That makes me
And it's because it's going fastest here where it's closest to the sun, and it has this very slow rotation.
Is that why they...
Look. Okay, there is a flaw with this black background action. Go ahead, what were you asking, Satish?
Is that why they say or is that how they explain like that missing chunk of rotation?
No.
Like, because it's pointing one direction.
Oh, that's I need to go around the circle. Okay, it's orbiting so slowly. Okay, going from here to here, it's done 1/4 of a rotation. Keep going here, it's done 1/2 of a rotation. Keep going here, it's done 3/4. Keep going here, it's done 1. Woohoo! 1 complete rotation. Hasn't been a full day yet. Has the nose pointed back at the sun yet? No. So we're not through a day yet. In fact, we're not even through half a day yet because the sun has not gotten to pointing away from, or the nose hasn't gotten to pointing away from the sun yet. So we keep going. Here we've done 1 1/4 rotations. Here we've done 1.5 rotations, and now we've done half a day because now the nose is pointing away. So in one orbit, it did half a day, but it was 1.5 rotations. The second orbit, it will have completed 3 rotations and have a full day. So it does 2 orbits for 3 rotations, and the days is the rotations minus the orbits. So 3 minus 2 is 1. So in 2 years, you have 1 day. Very interesting. Okay, go home. I've got to go take care of a flat tire in my car, so I won't be around this afternoon.